Now, we've spoken so much about space and not much about time.
I like that. Go ahead.
Are observers necessary for time?
I don't think they are necessary, but they're very useful in the sense that they experience time, and they also tell us which part of space we have to consider. So if you are living somewhere, you can only observe a certain part of space, and there's a certain part that you cannot see. And it's certainly true that in the microscopic description or the fundamental description, there are parts that we observe and there are things that we cannot observe. Now, one of the nice things that I have been, studying myself a lot recently, but also that many other people have been looking at, is that you don't need time to even have time emerge. So we can have space emerge, but there's also time can also be emergent. It also emerges from entanglement in a very nice way. And this has to do with indeed saying, well, if I have an observer, he can only see part of the space, and I should say part of even the microscopic theory. So there's some part that he doesn't see. And in quantum mechanics, what happens is that you then can see only part of the say quantum information, the bits, but there are things that you don't see that are entangled with the things that you do see. So you can count again the amount of entanglement. It also means that the description of the things that you do see is not given in terms of, say, a wave function like what Schrödinger wrote down. It's more like a density matrix, a thing that von Neumann thought about. And a density matrix is really an object that allows you to think about time, actually, because a density matrix, one way that we think about time in quantum mechanics is that there's a relationship with energy. So there's some way that energy kind of plays a role in describing time. It's called the Hamiltonian, because that is sort of how it tells that time evolves. And this is actually possible to define also using entanglement. It goes under a name what's called the modular Hamiltonian, but this is the way that time emerges. So we have some way that time can be defined even without assuming that it exists. And there's a beautiful mathematical theory already about it that also von Neumann already developed. I'm talking about whatever, more than 50 years ago, where really there's lots of very precise mathematical equations that are telling us that just from studying quantum mechanics that we can define time. And actually, it goes very much in the same way that I had in my paper on entropic gravity. The way it goes is that I have this part that I observe, say it's the right part of the space, the left part of the space I cannot observe. If I just forget about this left part, the right part, is described not in a very precise state. It's not a quantum state, but it's this density matrix. And then there's a time flow that I can generate just from this separation. And I don't need actually to assume time from the beginning. There's something that time really emerges from this idea. And I think that language of quantum entanglement and quantum the space-time, how that emerges. This is really where recent advances, people, I have to maybe mention other people in this context. People like Jeff Pennington, who played an important role, Engelhardt, Longview. There's many people involved, young people also, at MIT, at Berkeley, at Santa Barbara, who are working on these ideas. It's a worldwide effort, and I think the language I just sort of am using here, which I'm sure that many listeners find difficult to understand, but it's something that our current discussions and even the conferences are about. We are using these ideas a lot, actually, about how time and space sort of had this microscopic description in terms of quantum entanglement.
When talking about entropy in Donald Rumsfeld, it was said that the known unknowns is related to entropy, but known implies an observer just when we hear the word known, like someone knows it. So there are two aspects of entropy. One is that it's observer dependent regarding a coarse graining, but then another is that it's somehow an objective partitioning. So I assume that you're thinking in terms of an objective partitioning. What is it that's determining this partition that nature uses?
Well, okay. Here I have to admit that the observer has to play an important role, because when we have a observer, he has access to a measurement apparatus or something like this, and you can do all your measurements. And that means you're going to be discovering more about what the state of the universe is. I mean, you can try to determine where all the things are located. You can do lots of measurements, but there are also things you cannot measure. And we have, and this also in space-time is connected to what we call the horizon. There's namely things you cannot observe are behind the horizon. There's some way that we have to split the space-time in the part that we can observe, which we call our observable patch, kind of what we call the observer's area, which we can see, but then its boundary is kind of then saying that there's things beyond that we cannot observe. And so this entropy that we are currently measuring is indeed about the things that we are not observing. And the nice thing about what we are discovering, which is kind of goes back to these laws of Bekenstein and Hawking and Ryutak and Yagi, is that this amount that we cannot observe is exactly measured by this area of the horizon. And I admit that in defining this very precisely, I think we need the observer by saying, well, we define what we know as the things that we can observe in principle. That's not like we have to observe it, but that we have to sort of at least be able to do this by some measurement. But then there's the part that we cannot never observe, and that part we then called basically the known unknowns, because there's some way that we can calculate or at least we have an estimate of how much is not known or not accessible to our measurement.
So the person listening, what if they're saying, just a moment, Professor, are you saying that I, as an observer, the gravitational dynamics depends on how I arbitrarily coarse grain, my choice?
No, this is not the case, because I mean there's some way that as I said, the actual thing that you are not observing or not know is more like a matter of principle. I mean, if I say you can in principle observe everything, I mean, there's some way that you can measure lots of things. If you decide now to want to measure the distance to a certain star very far away, and then you can in principle do this. But even if you decide not to do it, doesn't mean that it suddenly becomes an unknown. I mean, there's some way that we have to sort of say that information that is accessible or known in a certain way is what in principle can be measured. I mean, there's some observable part of the universe that indeed corresponds to the things that are, I would say, are known. So we do give, if we talk about observers, we give them lots of power in terms of being able to observe everything that they could in principle observe, in terms of at least our mathematical equations.
Do you imagine that gravity's attractive property is just statistical, and that it's just if you were to observe close enough or for long enough, you would see fluctuations? Some moments where it reverses or vanishes potentially.
Now, I don't have a theory that predicts any of that, but I do think that in quantum mechanics there is always fluctuations, but that the fact that gravity is attractive is a very fundamental fact, that it's not something that we're going to change in any way. But I do think that, as I said, that the gravitational laws can change in certain situations, and especially And this is one of the things I already thought about when I thought about this idea of entropic gravity. When the gravity becomes very weak, I mean, if you think there are deviations and they're very small, they're more easily seen when the gravitational force that we would calculate is not strong but very weak, because then these fluctuations or these deviations might actually exceed the actual strength of the gravitational force, and that's what I found so amazing when I learned about these effects we observe in galaxies. Is precisely when the gravitational force and the acceleration due to gravity becomes very small, that we are seeing these deviations. So it's related to the strength of the gravitational force when the deviations occur. And so you might say this is a fluctuation, but it's not like it's going to be suddenly repulsive. I don't think that is the actual change that is going on. But again, I don't have a full theory that explains or even predicts any of that sort.
Does entropic gravity, your version, have any bearing on the cosmological problem? The cosmological constant problem, sorry?
I think the cosmological constant problem, I think we can solve this. I mean, it's not like, I think the problem arises precisely if you start thinking about it in the way that Wilson did, by saying that the only fundamental scale is the scale at which we cut off things in the UV, in the very short distance, because then you expect this cosmological constant to be very large. I think our universe has another scale, which is a very large scale. And somehow this has to come into the microscopic description. I don't think we, in the end, will have to deal with this problem in any serious way. And I think even in ADS-CFT, which is this anti-de Sitter space, I think we basically already solved it there, because there we would have had the same problem as well, but we don't see it. And so there's some way that this problem, I think, I mean, maybe I should call it a red herring, because I think it's not something that we should worry us too much.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Something else you should know about is that if you go to their app, they not only have daily articles, but they also have long-form podcasts with their editors and writers. This is also available online. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount.